Welcome to Mission to Mars. This video will present the physical laws of space travel, along with the relative magnitudes of celestial mechanics quantities. These are the masses of the Sun, Earth, Mars, the mass of a space probe, the gravitational constants and parameters, astronomical distances among these four bodies, and their positions, speeds, accelerations, and gravitational forces. But before we delve into all of this, let's take a walk in the park. I would really like you to meet someone. Johannes Kepler, a renowned German mathematician, astronomer, and astrologer. He made remarkable contributions to the field of astronomy towards the end of the 16th century and the beginning of the 17th century. While he was residing here in Graz, Austria, he published his first major work on astronomy, a book by the title of The Cosmographic Mystery. It was the year 1596. In that book, he explains the geometric nature of the Copernican system and even attempted to provide a divine justification for such a system. In the year 1600, he moved to Prague, where he began to collaborate with the famous Danish astronomer Tycho Brahe. It was there that he developed his three celebrated laws of planetary motion. His laws expanded our understanding of the solar system, enhanced the Copernican system, and later they were derived through strict mathematical developments. Those laws provided the foundations for Newton's universal law of gravitation, which was published in the year 1697. Yet, it was here in Graz that Kepler conceived his initial ideas that later became his famous three laws of planetary motion. But what are Kepler's laws? First law: planets move on ellipses with the Sun at one of the two foci of an ellipse. Second law: equal areas are swept by a planet in equal times. Third law: the square of the period of one orbit is proportional to the cube of the semi-major axis of that orbit. We will now be able to connect Kepler's laws with Newton's laws. The concepts of mass and force permeate Newton's laws. By mass, we mean the amount of matter in an object. By object, here we mean a particle, which is a small mass, like a sphere with a tiny radius. A force is any physical event that can change the state of motion of an object. A force results from the interaction of such an object with one or multiple other objects. Let's state Newton's laws. The first law of Newton's dynamics is the following: in the absence of any force on an object, that object remains at rest or travels with a constant velocity. The second law of Newton's dynamics states the following: a force acting on an object induces a rate of change of the object's velocity with respect to time. The third law of Newtonian dynamics states the following: for every action force on an object, a reaction force always develops that is equal in magnitude but opposite in direction to the action force. Integrated with the laws of Newtonian dynamics is Newton's universal law of gravitation. It states the following: the force of attraction between any two bodies of masses capital M and lowercase m is equal to the product of these two masses and the universal gravitation constant capital G, and this product is then divided by the square of the distance between the centers of the two objects. The second and third law of dynamics, combined with Newton's law of universal gravitation, will generate Kepler's laws. It is this combination of Newton's laws of dynamics with Newton's law of universal gravitation that enables us to calculate the position, speed, acceleration of any planet and any space probe. These are the mathematical expressions of all of these laws. Second law of dynamics, the mass of an object times its vector acceleration equals the vector force imposed on the object. Universal law of gravitation, the force of gravitation F, which is a vector, equals negative g times capital M times lowercase m divided by the square of the distance between the centers of the two objects times ER. ER is the unit vector in the radial direction away from the center of the object that generates the force of gravity. The combination of these two laws gives us the following. Mass times vector acceleration of an object, such as a planet, equals directly negative g times capital M times lowercase m times ER, unit vector, divided by r squared. This mathematical expression provides us with the law of motion, for instance, of a space probe of mass lowercase m due to the force of gravity generated by a planet of mass capital M, such as Earth. The vector acceleration A of a space probe is the rate of change of the vector velocity v of that space probe with respect to time. This vector velocity is in turn the rate of change of the vector position r of a space probe with respect to time. The computational solution of this particular expression, again, mass times vector acceleration A, that equals negative g times capital M times lowercase m times unit vector ER over the square of the distance between the centers of a planet and a space probe, will provide the position, velocity, and acceleration of such a space probe. As shown in the animation, closed orbits can be circular and elliptical, depending on the initial velocity of the probe on an orbit. In the formula given above, the mass of the space probe lowercase m appears on both sides of the equation. Hence, both sides may be divided by this lowercase m. This results in the following simplified expression. The vector acceleration A of a space probe equals negative g times capital M divided by the square of the distance between the centers of the planet and the space probe times the unit vector ER. The importance of this simplified expression is that all space probes, large or small, will execute exactly the same orbits if they initially have the same position and velocity. The reason for this is that the mass lowercase m of the space probe is no longer in the governing equation. In that equation, capital G is the universal gravitational constant. It is equal to the following number: 6,6743 times 10 to the power negative 11, and that is in meter cubed over kilograms over second squared. In this example, capital M is the mass of Earth. That is equal to the following number: 5,97219 times 10 to the power 24 kilograms. The product Gm that appears in this formula is called the gravitational parameter of the planet. For Earth, Gm equals the following number: 3,986004418 times 10 to the power 5, and the units are kilograms cubed per second squared. The radius of Earth, modelled as a sphere, is accepted to be equal to 6,371 kilometers. The orbital height of a space probe, such as, for instance, the International Space Station, is 420 kilometers. It follows that the distance r between the center of Earth and the center of the space probe in this example equals 6,371 kilometers plus 420 kilometers, and that gives us 6,791 kilometers. Such a space probe would only take about 90 minutes to complete one revolution or orbit around the Earth at an average speed that equals 27,580 kilometers per hour. Think about it. An airliner traveling at such a speed would only take less than 4 minutes to travel from Vienna to London. By reference, the average distance between the center of the Sun and the center of Earth equals 150 million kilometers. The average distance between the center of the Sun and the center of Mars equals 228 million kilometers. It follows that in its mission from Earth to Mars, a space probe travels from the center of the Sun, from a distance of approximately 150 million kilometers to a distance of approximately 228 million kilometers. For the majority of the space probe journey, the dominant force of gravity is that of the Sun. This information is available at the links that are provided in this unit. In the next video, we will discuss the International Celestial Reference Frame, with respect to which we measure the positions, velocities and accelerations of planets and space probes. Thank you very much and goodbye. Dankeschön und auf Wiedersehen.